Hello again, everybody. This video is to finish off 6.3. It's the second part to solving differential equations. And we're going to solve a special type of differential equation now, and it's called the logistic differential equation. And so here's what it deals with. If you remember before, we solved differential equations that look like this. Okay. And hopefully you remember that these have a general solution always of some exponential function. All right, you don't have to do it in terms of e, but usually we find it easiest in terms of e, so we do it just like that. So many things in nature exhibit this type of growth or this type of decay. We've done a few of them. Radioactive decay we've done. Non-limited growth, if you have unlimited resources and how things grow. But anyway, not everything grows like that. All right, if you think about it, this looks something like this. And then it starts to get out of control. And it grows incredibly quickly. And as you can imagine, things don't grow like this normally. Okay, if you can think of, let's say for you biology people, if you're growing a culture of bacteria, you'll notice that the bacteria starts to just grow and grow, and it grows doubly. It doubles every generation. But eventually, it's going to stop growing because it's going to run out of food. All right, its natural habitat, its habitat that it's in, only can support so many things. So really what happens is most things have what's called a carrying capacity. And we're going to use the letter L to represent this carrying capacity. So most things grow like this. They start out exponentially, but after they get to a point, they start to level off and approach this carrying capacity. Now, of course, nothing's that perfect in nature. What you'll really see is you'll see it spike up and down above and below this carrying capacity. Or some type of habitat maybe, or some animal in a habitat will grow above this. Then obviously they're going to die off a little bit because there's not enough resources for that many. Then they'll spike below it, then they'll spike above it and below it, and it'll continue this process. But anyway, this is sort of the theoretical idea of what's going to happen with these populations that grow logistically. All right, so we see exponential, which still has importance. All right, but most things deal with logistic growth that looks something like this. And so we're going to talk about that logistic growth and what its differential equation looks like. So remember, we called this carrying capacity L. All right, that's the most the habitat can carry, can have in its habitat, and then any more bad things are going to happen. So the logistic equation, the differential equation for this particular model here looks like this. The rate of y with respect to time is equal or is proportional to itself. So far we look very similar to this, but we have another piece, times 1 minus y over L, L being the carrying capacity. All right, and so you can sort of see why this works. All right, the rate of growth depends on y, depends on how much there is. All right, and it also depends on 1 minus y over L. And once y gets to L, all right, if y ever gets to L, okay, and you can see if it does get to L, that would be the carrying capacity. But if y ever gets to L, you'll have 1 minus 1, which is 0, which would mean that this would be completely flat. All right, theoretically, it never gets to L. But again, we talked about in nature how things happen a little bit differently. But this is a pretty good indicator of what would happen approximately. Okay, so this particular logistic equation can be solved. All right, and so we're going to see what it looks like when we solve it. Now, you are not going to have to solve something like this just yet. You actually won't have to do it until we get to around chapter 8. But it's good to see right now. You can keep it in the back of your mind. But your goal is just going to be able to be, if you look and you see something like this, you should know what the solution type looks like. just like if you see a differential equation that looks like this, you should know the solution type is an exponential. All right, so let's go through how we would solve something like this. First of all, we want to separate the variables. So I'm going to multiply dt over here. I'm going to divide everything else over here. So that gives me 1 over y times, and I'm going to do a couple things right here. I'm going to get a common denominator between these two. So this is L over L. So I have L minus y over L dy is equal to k dt. So all I've done is I took this stuff here and I divided it to both sides, so it's now over here. And of course I get a common denominator within this part right here. So anyway, now I have this differential equation, and what I want to do is I want to solve it. I want to find the antiderivative of it. All right, but before we take the antiderivative, obviously the right antiderivative is going to be fairly easy. The left one is something that we've never seen before. So I'm going to do a little simplifying. I'm going to take the reciprocal of this and multiply it to the top and the bottom. And so what that's going to give me, that's going to give me L over y times L minus y dy. This may not look too harmless, but in its current form, we can't take the antiderivative of it. There really is no antiderivative of it. All right, you can try and use a u. It's not going to work for you. You can try and do some kinds of different types of algebraic substitutions. It's going to be ugly. It's not going to be happy. So what we have to do is we have to do what's called find the partial fractions for this fraction. And the idea in itself is not that hard. All right, and so what we're going to do, and I'm going to do it in a different color over here, is I'm going to show you what it means to find the partial fraction of something, or just what is a partial fraction. So here are two fractions, 1 minus y over L. Okay, and what I wanted to do, and what I did, is I found a common denominator between these two. All right, so what I did is I thought of this as 1 over 1, and I multiplied it by L over L. So that I got L over L minus y over L. And I brought them together, so it's L minus y over L. Okay, finding a common denominator, you guys are very good at that. But the idea is, can you go backwards? All right, can you split it up into two separate fractions? And sure enough, this one's very easy. Okay, you could just L divided by L and negative y divided by L. Could have got back to the original one. But it's not always so easy. If you look at what we have right now, we have L over y times L minus y. Is this possible to split it up into something over y plus something over L minus y? Now notice this. You have two separate fractions with different denominators. If you wanted to get the same denominator, you'd have to combine them somehow. And you'd combine them and they would look like this after you combine them. So the idea itself is not that revolutionary. Okay, it's saying, all right, we have a fraction with two factors on the bottom. There is a possible two separate fractions with those two factors as the denominators. What were their numerators? Okay, what is A? What would that have to be? And what would B have to be? Okay, and the idea is if we can separate this fraction into two separate fractions, we can then take the antiderivative of those two separate fractions. And so here's how we do it. If they were to look like this, and we decided, all right, let's get a common denominator between these two fractions, we would have to multiply this one by L minus y over L minus y. And we'd have to multiply this one by y over y. And you can see now that they both would have a common denominator then. All right, they would both have the y times L minus y as the denominator. And so the top would look like this. A times L minus y plus B times y. And of course that would all be over y times L minus y. So anyway, you can see that we would have the same denominator here. We want it to look like this with L on the top. But right now we have all this mess on the top because we don't know what a and b are. But it's very easy to figure out what they are. We know that a times L minus y plus by must equal L because that's what we have as our numerator. So if we do a little multiplying through, AL minus AY plus BY equals L. Notice in order to equal L, we can't have any Y's. Notice we have a minus AY and a plus BY. What that means is that A must equal B so that the Y's would go away. Okay, because these Y's have to go away in order for us to only have L on the top. So what we have then is we have AL equals L or A equals 1. And since A equals 1, we know that B is also equal to 1. So what that means that is if we want this particular fraction to be split up into two fractions, this would have to be 1 and this would have to be 1. And so that gives us, on the left now, we have the integral of 1 over y plus the integral of 1 over L minus y dy equals the integral of k dt. So that process is called partial fractions. That's something that we are going to do, but we're not going to do it until chapter 8. But anyway, you can see it's not that difficult. It's definitely possible. We'll get to a little bit more complicated ones, but this is sort of the idea of how we do this. Now, let's get back to this particular problem and let's take some antiderivatives. Antiderivative of 1 over y is natural log of y. Antiderivative of 1 over L minus y is minus natural log of L minus y. And the antiderivative of k dt is kt plus c. So a little bit of simplifying here. This part is a little bit abstract, I guess, and maybe you might think it's pointless of why we're doing this. But what we're going to do is we're going to multiply both sides by -1. So that becomes natural log of L minus y minus natural log of y equals negative kt minus c. All right, you'll see why we did that in just a second. On the left, I'm going to simplify a little bit more. It's going to be natural log of L minus y over y, properties of logarithms. And now I'm going to try and solve for y, so I'm going to base e both sides. So I'm going to get absolute value of L minus y over y equals e to the negative kt minus c. Okay, with that said, I am now going to sort of separate this. I'm going to separate e to the negative kt and e to the negative c. I'm going to make it e to the negative c times e to the negative kt. Think of it like that. And so what I'm going to do is I'm going to this is just a constant, some constant, I don't know what it is, but I'm going to let that be plus or minus b. So b equals plus or minus e to the negative c. All right, and that deals with the absolute values. Finally, when we want to solve for y, multiply both sides by y and add y. So I get L is equal to y be to the negative kt plus y. Factor out a y from this and divide, and I'm going to get L over 1 plus be to the negative kt is equal to y. B could be positive or negative, remember. All right, so we just solved this differential equation. Took a lot of work, but we made it through. And if you notice what this is, and hopefully you remember this is one of those, back from pre-calc, one of those 8 fundamental functions that you have to memorize and what they look like and what they are. This is a logistic function. L being the carrying capacity, how much you can hold in a particular environment or habitat. K is a growth rate of some sort, and B is a coefficient that affects the growth rate as well. All right, but this is a logistic function. So what you need to know that this differential equation, ky times 1 minus y over L, is the differential equation for a logistic function where L is the carrying capacity, negative k is the growth rate, and there's some b value which you would have to figure out based on information given in the problem. All right, but anyway, this is the solution to that type of differential equation. And for now, that's something you're going to have to memorize. Or, I mean, if you don't want to memorize that, you can always just know you can do this by partial fractions. All right, but if you didn't enjoy the partial fractions that much, just memorize that for now that this is the solution to that differential equation. All right, now to some problems. All right, let's take a look at this problem. So this is obviously a logistic function. We've got 3,000 divided by 1 plus 14e to the negative 0.3t. And so the question is, we have a couple questions. What is k? Number one. And hopefully we can see that k right away is that k is equal to 0.3. Okay, based off what we learned before, it's L over 1 plus BE to the negative KT. So k is obviously 0.3. That's our growth rate for this logistic function. Okay, the next question is, what is the carrying capacity? All right, that's pretty easy too. It's 3,000. It's whatever number's on top. Third question is a little bit more work involved, but it says, what is the initial population? Well, the initial population happens at p of 0. So what we need to do is find p of 0. And this is just going to be 14e to the 0. E to the 0 is 1. So we have 3,000 over 15. And 3,000 divided by 15 is 200. So our initial population is 200, whatever it's modeling. I don't know, wolves. Wolves are always a big one. Whatever you want, though. Rabbits. But then the next question. When will t equals what when the population is at 50%? Sorry, 50% of its carrying capacity. So how long will it take for this population to grow to 50% of 3,000? So what we do in this situation is we set it equal to 50% of 3,000. So 1,500 is equal to 3,000 divided by 1 plus 14e to the negative 0.3t. And we solve. So solving this is not that difficult. I know that it looks a little tricky, but as long as you understand the properties of exponential functions and logarithms, just basic algebra, it should be okay. We're going to multiply both sides by 1 plus 14e to the negative 0.3t. So when we do that, I'm just going to distribute the 15 through to this when I multiply it through. So I get 15,000 plus 14 times 15,000, 21,000 e to the negative 0.3t equals 3,000. I'm going to subtract 15,000, 21,000 e to the negative 0.3t equals 15,000. Oh, yeah, 1,500, sorry. I misspoke there. I'm going to divide by 21,000. E to the negative 0.3t is equal to, outside 2 zeros, and we get 14. Take the natural log of both sides. And divide by negative 0.3. I must have done something wrong. Let me check real quick. Oh, I see. This isn't 14, it's 1 over 14. Hopefully you caught that. So let's start from there. Negative 0.3t equals 1 over 14. Now we'll take the natural log of both sides. And so I get negative 0.3t equals negative natural log of 14. Okay, natural log of 1/14 is the same as natural log of negative 14, or negative natural log of 14. Hopefully we're good on that by now. And when we divide, we get 8.7969 years. So it'll take that long for it to reach to 50% of its carrying capacity. All right, very good. Finally, I'm going to ask you one more question about this particular function. What is its differential equation? Okay, and hopefully you remember that these differentials have this particular form. This is in terms of p, so dp over dt is equal to ky times 1 minus y over L. We know what k is and we know what L is, so really the differential is 0.3y times 1 minus y over 3,000. And so that would be the differential for this particular function. All right, very good. We're going to try one more problem and then we'll be done. Okay, last problem. Find the logistic equation that satisfies the initial condition. Oh, and I forgot to give you the initial condition. Here's the initial condition, 0, 4. So your initial population is 4. So here we go. This doesn't look like some of the logistic differential equations that we've done before, but it will. What I'm going to do is I'm going to factor out a 4 over 5y. That's going to leave me with 1 minus, and let's see here. Factor 4 out of 5 out of that, and we will get y over 120. Okay, if that's a little confusing to you, you can sort of think of it as factoring out a 0.8. And you get y over 120. So we know a couple things now. We know what k is. K is 0.8. We know what L is. L is 120. So we can write our differential equation, or our logistic equation. So we get y is equal to 120 over 1 plus b e to the negative 0.8 t. And so we have almost everything figured out except we don't know what that b value is. But we do know that when we plug in 0, we are supposed to get 4. So let's do that. Let's set it equal to 4 and plug in 0. 120 over 1 plus, when I plug in 0 up here, it's going to be e to the 0. E to the 0 is just 1. So it's just going to be 1 plus b on the bottom. Multiply both sides by 1 plus b. We get 4 plus 4b equals 120 minus 4. And divide by 4. And we get 1029. So b would be equal to 29. And so what we're left with is y is equal to 120 divided by 1 plus 29 e to the negative 0.8 t. And there is your logistic equation that satisfies that differential. So you can see you don't have to remember the partial fractions, antiderivatives. We just know that if something looks like this in this particular form, we know that that's a logistic equation, with this value being the carrying capacity and this value being the growth rate on the exponential in the denominator. So that is all for section 6.3. We're actually finished with section 6.3 now, and so you should be able to do all of the homework. I hope you have a fantastic day.